Hello, welcome back to Learn It from a Layman. I'm Carl Christensen. I'm back with Matt, and for those of you that have been listening to our podcast for a while, you're already familiar with Peter Vogel. And if you don't know Peter, you need to go back and listen to our quantum physics podcast and our relativity podcasts. But Peter, welcome back to the podcast.
Thanks. It's good to be back.
So how's so for those of our listeners that don't know you yet, Peter has his majored in physics in college, but is now becoming a dentist. Where are you at in that process, Peter?
I've got a year left as of next month, so I guess a year and a month left. But
okay, awesome. So almost the home stretch here.
Yep.
Cool. Well, good luck. And I'm sure you'll be a great dentist, but right now, today, we're going to be discussing the basics of electromagnetic forces. And so we've done podcasts, and we did a podcast a couple of years ago about the electromagnetic spectrum, and I'm sure we'll touch on that as well. But today we're going to be talking a little bit more about what electromagnetic forces are, electromagnetic fields, that type of thing. So for the layman, Peter, could you just explain what an electromagnetic field is and just the basics of, pull apart the word electromagnetic and make it make sense for a layman?
Yeah, I mean, pulling it apart is probably the first place to start. Electric and magnetic fields are two different kinds of fields. They don't affect each other, but they are related to each other. So I think it would be starting out with electrostatic fields. It's when electricity isn't moving. So you have like a charge. It can be like an electron that's sitting out in space, for example, and that electron will generate a field around it. And that field is just like, the field is where if you were to put a charge into that field, it would determine how much force would be placed on it, whether it's a proton or electron, or how charged that is would depend on how hard it pushes or pulls on it. But an electrostatic field is a field that is just like, typically when they describe them in physics, they talk about like a topographical map where you have a higher mountain, the higher your electric potential is. Electric potential is just like how potent the electric field is, basically. So a really basic electrostatic system would have a charged particle sitting out in space, and you would, if you were to look at that field from a electric potential point of view, you would see a big mountain that would fall off exponentially as you get further away from it. And then there's a magnetostatic field, which magnetic fields are different. Magnetic field has there doesn't have to be any charge in the field. It's just magnetic. So magnetic field runs from north to south, as pretty much everyone is aware of. And it looks like, when you draw it out, it's an arrow that shoots out of the north and then curves around and comes back into the south end of the magnet. So some people are seen where you like have iron filings next to a magnet or something, and you'll see them all like line up along the magnetic field lines. If you ever want to do an experiment, you can take a magnet and put it under like a plastic sheet, and then dump iron filings on top and shake it around, and you'll see what the magnetic field looks like. It's kind of cool.
Now, when you say north and south in that context, you're not actually talking about the cardinal directions north and south. These are the labels that are given to different poles of a magnet, regardless of their orientation relative to the compass.
Yeah, they're just labeled that because that's what it does on Earth. So, I mean, Earth has a north and south end, and that's where they started with magnets, basically. But
okay, I got two questions.
Yeah.
One is, so we started with electrostatic field, so is that, so when people rub a balloon on their head and then you can stick the balloon to the wall, is that static electricity? And is that
Yep.
the same as a static electrostatic field or whatever?
Yes. So static electricity means static is the word for motionless, right?
Right.
So static electricity in an electrostatic field would be basically like your charges aren't moving. The point where electricity and magnetism become related is when electrical charges start moving. So I have a couple more thoughts on that. Let me just finish
Sure.
those out real quick.
Sorry,
And then I'll come
yeah,
back
not
to this.
to hijack the
No, you're
conversation.
good.
Go ahead.
So like an electrical field, basically it's a space, an electric charge will push or pull electric charges that are in that field. And then a magnetic field will, it's generated by moving electric charges. So kind of like you were talking about, you have a static electric charge, that one is just purely an electrical field. And then as soon as charges start moving, now you move into an electromagnetic field because you're starting to whenever a charge moves, if you have like an electron moving through space, it'll generate a magnetic field as it moves. So you can't have a magnetic field without electricity. And magnetism, if we really get down to it, if you want to go all the way down to the quantum realm again.
We do.
So magnetism gets generated when you have, we can talk about pi orbitals and sigma orbitals and electron density clouds and all of that, but when it comes down to it, that is just a lot of math. The simplest way to think about it is every atom has electrons that are in two different states. They're in an up or down spin, is what you call them. And then materials that can have magnetic properties are materials like atoms that will have a spin that is uneven. So if you have all of the atoms spinning in one direction, or all of the atoms' electrons spinning in one direction, this is kind of dumbed down. If they're quote unquote spinning in one direction, then you would have a really strong magnetic field, but they're always paired. So usually you'll have one up and then one down, and then one up and then one down, and up and down is denoting the spin, meaning basically what direction they're spinning around the atom. And so, if they're unpaired, so if you have like 21 atoms, for example, you don't have the same number of up and down spins, which means that one electron is out of balance, which generates a magnetic field because you have a moving electric charge that isn't canceled by the other electron.
Okay. Now you said for stronger magnetic fields, that just means more electrons that are out of balance. And how do you get out of balance?
So it's just with any atom, the metals are more magnetic typically because I guess something that is a stronger magnet has more magnetic dipoles that are in one direction. And a dipole just means what direction that atom is pointing, basically. So if you have, like, we'll just, for simplicity's sake, say you have 4 or 10 atoms in a bar, and 5 of them are pointing one direction and 5 of them are pointing the other, then that bar will have no magnetic properties. But if you were to get all of them pointing in the same direction, it would be a stronger magnet. So really strong magnets are materials where they've oriented all of the dipoles. And a dipole is just like the north and south end of a magnet, where they orient all of them in the same direction. So like a neodymium rare earth metal, they've managed to lock all of those dipoles in one direction. And you can adjust the way that those dipoles are oriented, typically by heat and even just like hitting something. So like making a magnet can be done by just like hitting a piece of metal while it's hot, and then putting it in a magnetic field, and those dipoles all the atoms literally just vibrate and turn until they're facing the same way as the magnet that's nearby. If that makes sense.
It does make sense. Okay, that's cool. Okay, so then you explained magnets, which is really useful because that's something I wanted to better understand. I feel like I've got a better grasp on it, even if only a layman's understanding. But so now we've got a magnetic field, we've got a new magnet, these aligned on off balance electron charges that are creating this magnetic field. And the idea is electromagnetic field is you've got the electricity, the static electricity sitting in the static field, and then you've got a magnetic pole, and so it's gonna pull that charge, that electric field charge. Is that right?
Sort of.
Okay.
So electricity and magnetism don't interact at all until electricity starts moving. So if you had a magnetic field and you put an electron in a magnetic field and it's just sitting right there, absolutely nothing will happen to the electron. But as soon as the electron starts to move, that's where they start interacting.
So is it fair to say that when you have an electromagnetic field, you can't have a static electromagnetic field? There has to be motion for it to be electromagnetic. Likewise, you can't have a dynamic electric field without the magnetic field that goes with it, because when it's moving, that's where they're together. When they're static or not moving, that's where they can be apart.
Yep, exactly.
I think I just said what you said over, but whatever.
No,
we learned through repetition.
Well summarized. Yep. So when charges are basically an electrostatic field has nothing to do with magnetism. However, as soon as charges start moving, which charges almost always move, then you start getting magnetism. So if you rub that balloon on your head and it gets all staticky, and then you move that balloon, you're starting to make magnetic fields. You're starting to make magnetic waves, honestly. But.
Okay. And I guess that's where we go from here now, right? So we've got kind of a basic, well, I have a basic, you guys have a better understanding, but I have a basic understanding of electrostatic fields, magnetic fields, and that in order to become an electromagnetic field, there has to be movement involved, and that movement is waves, right? So now we're talking electromagnetic waves. Can we start? So why does it travel in waves, and is that just the property of the let me not jump it. Why does it travel in waves?
Okay, well, that's why it travels in waves is kind of a long explanation, but I'll see what I can do. So electromagnetic waves are light, right? Light is what we see, but there's you guys have done a podcast on this, but there's a whole lot of electromagnetic waves that are just outside of the visible spectrum. So there's a certain window of those electromagnetic waves that our eyes are capable of seeing. And then on either end of those is where there's a whole bunch of other waves, such as radio, microwave, X-ray, gamma. They're just different wavelengths that our eyes aren't designed to be able to see. So that's where we start off. And then the first law of thermodynamics basically states that energy can neither be created nor destroyed. So when light is created, mass is converted into energy. That's the whole E equals mc squared equation that Einstein came up with. And so, okay, those are all important things to understand. So once you have the energy that was created from mass, now you just have a photon. And because that energy can't be created or destroyed, it has to go somewhere, which means that a photon you initiate it by initiating some sort of electric field, right? So, and it's an electric field because it's an alternating electric field that you're creating, and that field it's a photon because it's an alternating electric field, and that electric field looks like a sine wave. For those of you who may not know what that shape is, it goes up and then it goes down, and at some point it crosses the zero line, and the zero line would be where it has no energy. So it just goes up and down and keeps crossing that zero line. And going back to that first law of thermodynamics, where your energy can't be created or destroyed, it doesn't make any sense that you're going to having energy to no energy to having negative energy compared to where you started back to having zero. So that energy is being transferred from being a magnetic or an electric field into becoming a magnetic field, because as we talked about in the previous part, whenever you have an electric field change, you generate a magnetic field. So your electric field gets generated right at the start after your mass is converted into energy. You have just like a bump of energy in an electric field, and then that electric field collapses, and it collapses into the magnetic spectrum. You could describe it as that. And then that makes a magnetic field that bumps out, and then it starts to collapse into the electric field again. And as that goes, it propagates back and forth, and they're just feeding off of each other. And then, let's see, that can propagate through space because it's just energy. Energy can go back and forth, and it's super efficient because there's nothing that's taking energy away from it. Yeah, I don't know if that made any sense. That was probably a little in-depth.
I was candidly, I for a while I was like, I'm way in the deep end here. I have no idea what's going on, but I think I just held on just long enough that I think I understand. So essentially, you're saying it travels in waves because that's what, like, electromagnetic fields, by definition, like that's the way that those fields interact is like what you just described, like that sine wave up and down, and in order to adhere to the law of physics and thermodynamics, those fields have to do that interplay, and that's what happens is a wave.
Mm-hmm. And light is purely electric. It's purely an electric field whenever you hit a maximum on that sine wave. And then once you hit zero, it becomes purely a magnetic field. So it's really just like, it's like if you take a string and you shake it, you send a wave down that string, and that wave, the energy is traveling through the string. But in this case, it's traveling through an electromagnetic field.
I've now understand something fundamental that I didn't before. So this is great. Okay, great. Let's you gave some examples, like obviously the electromagnetic spectrum's got a bunch of the different wavelengths and all those things to give us different variety of waves that we described and have talked about in previous podcasts. Something we didn't delve into a lot, though, is the medium through which they travel and how that affects the waves as well. So if I've got just, let's say, visible light, for the sake of being pretty light, something more familiar to the average man, when I hit water, I know that my light is this electromagnetic radiation is being affected. How does that work, I guess, across the spectrum, and why is it that different mediums affect different types of electromagnetic radiation in different ways?
Yeah, that one question is like a whole field of physics, but
okay.
Right, we've got a few minutes left on this podcast. So.
Yeah, come on, Peter.
No, it's okay. I'll do what I can here. But electric fields. So electric fields and magnetic fields travel through different mediums in different ways. So let's talk about magnetic fields first, maybe. Magnetic fields can be transmitted through metal objects by realigning the magnetic dipoles, like we talked about before. So when you bring a magnet close to a metal object, the dipoles in the metal object are kind of like they are forced to turn to orient themselves with the magnet that's coming close to them. And as those dipoles turn and they all become in the same, or they all point in the same direction, they're transferring that magnetic field more efficiently than it would have in just normal space, right? So if you take a magnet and you put like a metal rod on that magnet, then your magnetic field is kind of extended to some degree. because it's able to travel through the metal rod better than it's able to travel through space, because it is able to like rearrange each of those dipoles and transfer its field further. And then as soon as you pull it away, if you pull that magnet away from the metal bar, then all those dipoles, they want to be how they were before. So they all will like snap back to where they were before, and that metal bar will just go back to being an iron bar or whatever it was you were holding up. You can, as we talked about before, make that metal bar into you can make it into an actual magnet by physically, like, it's kind of a weird interaction of like the atomic level with what you see every day, where you can just like bring it down to the dumbest way, hitting like rocks against things back to the caveman age. But if you start hitting it, each of those dipoles kind of relaxes, and the more you hit it, the more that those atoms reorient themselves while they're in that magnetic field. And then when you take that bar away from the magnet again, all of those dipoles, because they've just either, if you heat them up or if you just literally smack it with a hammer or a rock or something, those dipoles won't snap back to where they were quite as much. So
okay, so literally, like if I have a strong magnet and I want to make another magnet, I can take a piece of metal, a metal bar, metal rod, or whatever, put it next to the magnet and just whack on it for a while, and it becomes a magnet.
Yeah, exactly. So as long as you're deforming the metal to some degree, it'll start, like those atoms will start to reorient themselves to be in basically in accordance with what the magnet next to it wants it to be. So
well,
if
the magnet next to it, if you start just punching rocks together, I don't know that you're going to get what I think Carl was getting at. I don't know.
No.
Yeah, I mean, you could hit your metal bar with a rock, but it has to be the appropriate material, right?
Yeah, if you take two metal rods that are not magnetized and start crushing them together, are you going to build a magnetic field that way?
No, because you have to have a magnet in the first place, right?
Okay.
The magnet will,
like
you have to put the magnet next to it. Yeah, if you put the magnet next to it, then all of those dipoles in the rod that wasn't a magnet will kind of turn to try and look like the magnet next to it.
Yeah.
And that's where you just beat the crap out of the metal rod until it looks like until basically it complies with what you want it to do. So
awesome.
Can we talk about that, or rather talk about magnets really quick, though? Like, as in, there are some things that are just magnetic, other things that can become magnetic. What makes something inherently magnetic? Yeah. Yes. Thank you, Carl.
Okay, I was just trying to get, needs to be some comedy.
Yep.
Okay.
To be magnetic, we go back to the thing we talked about at the start, where we go all the way to the quantum level with electrons that are spinning in one direction or the other, because magnetism is only generated when an electric charge moves. So if you have an atom and you think about it like the sun with the planets turning around it, if you have 5 electrons going in one direction and 5 electrons going in the other direction, then they cancel each other out. And that atom has no potential to ever become magnetic, because it has an even number of electrons, basically. When you get to atoms that have an uneven number of electrons, then you start to have the potential to become magnetic, because you can have 4 going in one direction and 5 going in the other. And now you have a net 1 electron going in one direction, which makes it capable of becoming magnetic. But it does get a little more complicated than that, because you have ferromagnetic, you have diamagnetic, and there's one more where those are kind of complicated, because sometimes magnets, paramagnetic was the last one. They do different kinds of things. For the most part, what people know about are ferromagnets, though, where they do the same thing. Like, they just have a north, south, and they do what you would think would happen with a magnet.
Okay. But you were, sorry.
No, sorry. What were you going to say?
Oh, I was just going to take us back. So I don't know if you were describing how magnetic fields can travel through metal, for example, but then there are other types of electromagnetic radiation that don't travel well to particular types of mediums, right?
Yeah. So, I mean, with the magnetic one, we talked about using a metal bar. If you stick a rock next to it or water or something, it won't change your magnetic field at all. It'll just be exactly the same, except that there's a rock next to it. An electric field does different things. We're talking electrostatic field because we're going to just the very basic things right now. With an electric field, it decreases when it passes through materials called dielectrics. Dielectric, in its most basic form, is just an insulator. So like rubber, plastic, things like that. So this is a useful thing when you have things like a capacitor, for example. A capacitor is, in its most basic form, two plates, where you have one plate that's charged negatively and the other plate that's charged positively. Or you charge one plate negatively, and by charging it with a negative charge, you push all the electrons out of the plate that's next to it, because electrons don't want to be next to each other. If you put a dielectric or insulator between the two, you're putting something into that electric field, and it makes it harder for those electrons to push on the other plate across from it. But there are other things that electric fields do travel more easy. Well, let's see. So other materials, if you touch the plate, or if you touch something that's charged with water, you mentioned water, it'll just go away because the charges will jump into the water and be carried away. They travel through air, okay, and then an electric field in space would be kind of the most pure. Everything has what was the word I used? A dielectric constant to it. So air has a dielectric constant, rubber does, plastic, and each one of those types of plastic and rubber have a different one. But yeah, you're getting all sorts of hard things here into this podcast. But
that's what we like to do. We take the layman and we really educate them, or at least we try. Or you try.
Electric. Well, I think you guys have a lot of them too. I've listened to some of them. You guys have lots of good podcasts, but not the ones that involve me for the most part.
Right. There's a reason that people are listening to this podcast, Peter, more than any other podcast. So, okay, so you
guys, not me though.
So in space, you have a pure electric field. So if I'm talking electricity, like in my house, electricity, that is purely electric field, not an electromagnetic field?
No.
Yeah.
Because when you're using electricity in your house, you're using electrical flow. It's charge is moving. If charge was not moving, then none of your appliances would actually do anything.
Okay. Yeah. And so I have an electromagnetic field traveling through usually wire, right?
And all through your house right now.
Right. And what is that? An electromagnetic spectrum, that is what?
So it's not so much that you have an electromagnetic field traveling through your wires. You have electrons traveling through the wires, and those electrons generate an electromagnetic field around them. So every wire that goes through your house has an electromagnetic field that kind of circles it, if that makes any sense. So if the electrons travel straight, then you have a magnetic field that makes a circle around the wire. And anytime, like if you put two wires next to each other that are traveling in the exact same direction, they'll repel. So the wire next to the other wire with a current traveling in the same direction, those wires will push each other away because of the magnetic field that they make, not because of the electric field. And then if you turn them around, then they'll attract to each other because of the magnetic field they create.
I think the other part to be clear about is the distinction between an electromagnetic field and electromagnetic radiation. The radiation is the waves, that is the light, the X-rays, the gamma rays, the whatever rays. The field is not that the same way.
Yeah. Typically, we don't really talk about an electromagnetic field. Electromagnetic field just basically means it's complicated. It means that there's both an electric and a magnetic component. But when you work with electric and magnetic fields in physics, you work with them independently, and then you figure out how they interact after that.
Okay.
So you work with an electric field and you work with a magnetic field, but you don't work with electromagnetic fields. An electromagnetic field just means that both are involved in that area in space.
Okay. Let me see. So electricity. So for example, so we got electricity inside the house. Obviously, you talked about it travels through wires, and you have two wires, they push apart or pull together, but they're all insulated, right? And that's the idea, is you want to disrupt that magnetic field between them.
No, because as we talked about, the magnetic field, you can't stop it, basically. It just goes right through the insulator on the side. Okay. All the insulator, like the plastic or rubber or whatever they put around your wire, all that does is it just, if you touch two wires together, it keeps you from short circuiting something. It keeps it from running current or running electricity through things in a way that it shouldn't be run.
Okay. So the magnetic field's going to do what it's going to do.
Yeah.
Yeah. Right. Unless you put another magnet in there to perturb the field.
Okay.
Yeah, that's true. There are some cables, they're called coax cables, that they use for like TVs and stuff, because when you start messing with magnetic fields around your TV, you start messing up the signal that your TV is getting. And they use something called a coax cable, where they run a current in one direction through the central cable and a current in the opposite direction through like a tube that goes around that cable, and those magnetic fields will counteract each other, so that outside of that wire, it looks like there's not a magnetic field being generated around the wire, if that makes sense.
The fun experiment is to take an old TV and an old set of speakers and place the old speakers, which have magnets in them, on top of your old CRT cathode ray tube TV, and then watch as the image at the top where you've placed the speakers changes color, sometimes permanently, which may have happened to our TV at
I was
one
going to
point.
say, that sounds familiar.
Yeah.
It'd be also interesting to play music through your speakers while your TV is on, because then your field would change the whole time.
Oh, yeah.
Wow. Okay.
Sound at that point.
Okay. So yeah, I didn't know that about coaxial cables. So with the so another thing that I know the layman has frequent interactions with is lightning, right? That's an example of an electromagnetic field that's generated in the clouds and then needs to release its charge, so it hits the ground, right?
Lightning is nature's capacitor, basically. You get the charge builds up in the clouds, and then the electrons are you made a static field, so you made electrons in the sky, and that are just, for all intents and purposes, they're not moving fast enough to make a strong magnetic field, but the electrons are in the sky. The Earth, those electrons in the sky push the electrons on the Earth out of the way, so the ground starts to look more positively charged, and then once the charge gets big enough, you have an arc, just like if you put a battery next to another or like you put two charged wires next to each other, eventually, if they get close enough or there's a high enough voltage, they'll jump between the two.
And that's why if
basically,
you're close,
yeah, it's just an arc.
If you're close enough to a lightning strike, your hair stands on end. Is that because of the magnetic field that's generated then, or is that the electric field that's still also affecting you, even if you're not directly struck?
Yeah, unless your hair is made of metal.
Yeah.
Okay, so I guess my
Iron Maiden or something.
Okay, so not the magnet as much, but there would be magnetic field generated. I'd imagine for a split second it'd be pretty strong, right? In the lightning strike.
Yeah, when it actually arcs, you generate a magnetic field. What you're feeling though, when your hair starts to stand on end, if you're close to where lightning is going to strike, is when you have a strong magnetic field. So you have a whole bunch of electrons built up in the clouds. Those electrons, you have electrons in your body, and electrons don't like to be next to electrons. So you're standing on the ground and all the electrons in the sky are pushing down on all the electrons in your body, and they're trying to push them into the ground. So all those electrons are just being pushed out of you. And now your hair is positively charged and the sky is negatively charged, and your hair starts to so positives and negatives attract. Your hair starts to get pulled up towards the sky because of the electric field or the electric force that's being applied to you because the sky pushed all of your electrons out of you. Which is a bad thing for you because it gets you even closer and it makes that arc easier. And
okay.
Yeah. So you start to feel that tingly thing and your hair starts to stand up because you are what is having its electrons pushed out of. They're pushing out of you.
Wow. Okay. Can I go? Let me revisit the electricity inside the house again. Once again, so most of the wires that we have inside the house, electricity. Like if I'm doing some type of basic electric work in my home, I see like two wires, usually, or three even together. But you talk about how like they're either going to like pull together or repel each other. Is that so? I know that there's also like a ground wire. What is a ground wire, and what does that do as far as electromagnetic field is concerned?
Electromagnetic field isn't affected by a ground wire. Because
Okay.
once again, we don't really work with electromagnetic fields. That's just
saying
that both of them are. For the most part, you work with one or the other, and saying that an electromagnetic field is just saying that both are involved somehow.
Right.
However, with wires in your house, typically it is labeled positive, negative, and ground. Really, you just need. So the ground is, you have something called alternating current in your house. Alternating current is a whole different topic. There's a lot of cool history that could be a different podcast entirely, where you talk about alternating current and direct current and the history behind all of that. But
or a band like AC/DC.
Yeah. Or AC in your car, where you have alternating current that you turn on, right?
Yeah, exactly. That's right along our level here.
Right?
You're speaking my language. Okay.
Yeah, so ground in your house, though. Ground is, there's literally a part of your house that goes into the ground, and it's something to keep you safe. It keeps the electrical energy from getting too high. Your electricity runs into the ground eventually, basically, because it all wants to equalize. Nothing likes to have a positive charge or a negative charge on it. So when you're done using your electricity is always trying to run into being at an equilibrium state where there's no positive or negative charge at all. And the Earth is just a big sink of sucking up electrical energy that we've created. So as we create it, the electrons, in the most basic term, will do what they're supposed to do in your house, and then they get released into the wild and stuck back onto Earth, basically, where they're happy again because it's mostly even.
Okay. So yeah, and I'm generally familiar, obviously, the idea that a ground wire is a safety precaution. I know that there are electrical appliances that do not have ground, a ground plug or something like they don't. And I assume that's just because the electricity consumed is just not significant. There's no real risk of overloading or the electrical current there or something like that.
No? Yeah, I mean, with alternating current, it's a little more complicated, but
okay. Well, we
that
don't have
might
to
be
go
a
into
whole
that.
different topic.
Yeah, let's get back into the physics of electric fields or magnetic fields. So I got off on this tangent of electricity in my house because it's interesting. But so is electromagnetic force. So we talked a little bit about, Matt was talking about how electric fields are different than electromagnetic radiation. So an electric field, and we talked about how different mediums affect it in different ways. How does temperature affect like an electric field or a magnetic field?
Temperature, this isn't the most exciting topic, but basically the higher your temperature gets, the less conductive your material gets. And the reason for that is in a wire, you have a bunch of, if you can think of it as a bunch of people passing an electron or passing a bucket of water down a chain. If everything is, when something gets hot, all the atoms start moving a lot and they're just vibrating all over the place. So if you think about our people passing buckets of water down a chain example, if everyone's just standing stationary in their perfect position and they just keep handing the bucket left to right, it all runs smoothly. But if you have everyone in that chain, like running back and forth and trying to pass the buckets, they're just like somewhere, like there's no like order to it. They're just randomly running around. And if they happen to come to the next person, then they hand them the bucket, but it stops being efficient basically. So temperature makes things vibrate. Vibration makes it less efficient because now it's not this structured
Is that
structured like system.
Well, does that have anything to do with why like people say, or I've heard this is also just a rumor, but like putting a battery in the fridge is good for battery life or something like that? Potentially unrelated, which is how I roll.
That has more to do with inhibiting the chemical reactions that cause your battery to lose its charge. Now, the thing that will make your item perhaps run more efficiently is to operate whatever thing you have at low temperature.
Okay.
Yeah.
So if that makes sense.
Yeah.
So like when your computer gets hot, your battery dies faster.
Right.
Well, or yeah, because I mean your material or your charges don't flow as well, is what you're saying, or what I heard.
So we should make people in Arizona move out because they're wasting electricity?
There are many reasons to make people move from Arizona, but yes.
Among the reasons to abandon Phoenix as a lost cause is because electricity does not travel well on hot day wires or super hot situation. Whatever temperature negatively affects the efficiency of the flow of electricity, essentially, right?
Mm-hmm.
All right. So
however, temperature in general doesn't. I mean, you can have a lower temperature that can make things more efficient. There's things called superconductors, which are really cool. They're super cool because they're superconductors, but
yes,
super cool in two senses because you have to literally super cool a superconductor for it to become a superconductor. So you can get these pucks of superconductive material, and if you pour liquid nitrogen on them, they go from being just a boring piece of ceramic typically to becoming something that has almost no resistance when you run electricity through it, which has some other cool effects when you have a magnet nearby, because if you supercool that superconductor and turn it into a superconductor next to a magnet, you get something called flux pinning, which means that the magnet and the superconductor will stay in the exact same orientation that they were when you cooled the superconductor until that superconductor ceases to be a superconductor. So you can take your magnet after you've cooled that superconductor and move your magnet and turn it upside down, and that little like puck that's sitting there will just float about 2 inches or however far away it was. And you can turn it upside down and spin it all around, and they'll just stay in the same position even though they're not touching, just floating there in space. It's really cool looking.
Wow.
But maybe that's a different topic too. I don't know.
No, that's cool. I like that. But you did mention flux, and I know we've already talked capacitors, so I think it's time to talk flux capacitors.
You know, pop culture doesn't have to come into everything, but
I mean, clearly it does. And I don't know, this Back to the Future count as pop culture, and nowadays, like, I don't know. Anyway, okay, let's hit a couple more questions here. So I'm not entirely sure I entirely understand the difference between an electric field or a magnetic field and electromagnetic radiation. Does an electric field, when it starts moving, when it becomes an electromagnetic field, that the electrons flying off of it are the electromagnetic radiation, or what is the difference?
So let's think about the word to radiate. Radiate just means it goes outwards, basically, right? So you can radiate positive energy, and you're just sending out positive vibes to the universe. Radiating electromagnetic radiation, all that means is you're sending out energy in the form of electromagnetic fields. So you're creating, as we talked about at the start, an electric field, which then collapses into a magnetic field, which then builds its electric field back up again. And that radiation is just those waves of those electromagnetic waves. We call them electromagnetic waves because they have both an electric component and a magnetic component to the wave.
Right. Okay. And so as it travels, it's traveling, and when it's traveling, it is radiating. Therefore, it is electromagnetic radiation.
Yeah, something radiates electromagnetic radiation, which means, so like the sun radiates electromagnetic waves, which means that it is just emanating, it's just shooting out a whole bunch of energy in every direction, and that energy is a photon. And I don't remember if it was on this podcast that we talked about photons being like a particle and a wave, but
right. I think that was we have talked about that before. I don't think it was this podcast, but if they want to know more,
no, we did. We totally talked about wave particle duality.
Yes, we did. We certainly did. We talked about wave particle duality and the basics of quantum physics, or whatever that podcast was. So with you've described very well, so that even I understand the difference, or why they travel in waves, why electric fields that turn into magnetic fields travel in waves. Is it just increased energy then that changes the wavelength and or amplitude?
Amplitude is directly correlated with intensity. So a really bright light has really large amplitude waves. And then a wavelength is inversely proportional to energy. So the higher the wavelength, meaning the longer a wave is, the less energy it has. So electromagnetic waves that have a very high energy have a very short wavelength, meaning the waves are very short. So radio waves can be miles long, where you have the peak of one wave and the peak of the next wave, meaning the peak of when it is in the electric field back to when it's at its maximum in the electric field again. That can be miles different, where it takes miles for the electric field to collapse into the magnetic and then come back into the electric field again. Whereas if you have other ones that are higher energy, that means it's a shorter wavelength. And that goes into things like gamma, X-ray, radio, or not radio, microwave, things like that are higher energy. Yeah.
And your higher energy waves travel better through more solid objects. Is that true? It's like X-rays, obviously you can look inside a person's body, for example, and under their skin or whatever, through some material, where like visible light, if I go behind a wall and I turn on a light on the other side of the wall, I'm not going to see anything. It's not traveling through any solid matter. So is it the more energy, the higher that wavelength, the more it can penetrate through solid objects?
I don't know if I'd go that far, because if you think about it, radio waves go through stuff pretty well too.
That's true.
I think it's more of so objects absorb electromagnetic waves depending on where the electrons fit in their orbitals. So we're going back to quantum. We go back to quantum a lot in this podcast for some reason. But basically, glass is transparent to visible light because the electron, there's certain states where you have more energy and less energy, and the electrons can only jump between those states. And light travels through glass because the atoms in glass have a gap between those two different energy states that isn't appropriate to absorb the amount of energy in the visible light spectrum, or the electromagnetic waves in the visible light spectrum emit. So it doesn't have the capability to absorb that light, and the light travels through glass, but it doesn't travel through brick. X-rays go through things because they're very, very high energy, which means that they're basically things absorb them, but there's just so much energy involved that it penetrates through it better. So in a sense, you could say that X-rays, gamma rays, things like that do penetrate better, but it's more because of the amount of energy they have than what part of the spectrum they're in, I guess.
Okay.
If you think about it, though, I think it's really fascinating that visible light and gamma rays and X-rays and all of that are all just, and radio waves, they're all just one spectrum. They're all the exact same thing. It's just how much energy they have. So the visible light spectrum, basically, as soon as you leave the visible light spectrum and start going higher energy than that, you get into UV, microwaves, and then you go to like X-rays and gamma rays. And basically, as soon as you leave the visible light spectrum, after purple light, even once you're in purple, you start to damage things like your body and skin and anything. Basically, purple light can damage you. Anything more purple than purple hurts you more. So you could think of X-rays as being very, very purple light to some degree, I guess.
Right.
And then infrared is not going to hurt you, and anything less than infrared. Radio waves are just very, very red waves to some degree.
And that's because of so it caused damage, like when you go to the dentist, for example, and you have to put on that. Is it lead? It can't really be lead, right?
Yeah,
whatever that
lead
vest thing is.
No,
lead?
It's actually lead. Yep.
Okay, lead vests they put on you in order to protect you when they're doing an X-ray of your mouth or something like that. That's because the electromagnetic radiation causes cellular damage. And is that because of the electrons or the energy?
The energy physically destroys the DNA.
Okay.
It doesn't. Wait,
Sorry,
what are you saying, Matt?
No, go ahead and finish it up.
Like the DNA, it doesn't happen very often that it will actually destroy the DNA, because the DNA is a very small part of the cell. And so the chances that photon will actually hit the DNA and damage cells in a way that it will have an actually large effect on your body is pretty low, especially with dental X-rays. There's not a ton of radiation that comes out of that. You get probably more radiation walking around outside than getting your dental X-rays. And I think the lead vests are kind of a joke in dentistry, to be honest, because the amount of lead that's in one of those is pathetic compared to an X-ray. So unless you want to wear something very, very thick that would crush you, you're not
really doing anything. It's more for show than is what you're saying.
Yeah, it makes the patient feel good. And there's actually some studies that came out recently that it is no longer required in dentistry to wear a lead vest, because it's just like people are realizing that it's not effective. Yeah.
Okay. Oh, good to know. Look, we just got insight into dental practices as well in a podcast about the electrical and magnetic fields. We now understand something about the dentist. It's wonderful.
Hey, can I ask a question? You mentioned how higher frequency waves are generally higher energy waves. And while I get that, how does that relate to when we talk about a wave being higher energy? We're not talking about amplitude here. We're talking about something else. Could you elaborate?
Energy, yeah. So amplitude is intensity, as we talked about. And then you used the term frequency. We were talking about wavelength.
Yes.
Wavelength and frequency. Related. You understand.
Yes,
clearly,
I do.
But just
I should
for
be
everyone
consistent.
else out there. No, you're good. For everyone else out there, frequency and wavelength are inversely proportional. So when you have a high frequency wave, you have a low wavelength wave. But what you were saying about the energy, the equation that governs that is E equals HF, where H is a constant, it's Planck's constant, and then F is the frequency. Or it can also be E equals HC over lambda, where lambda is the wavelength. None of that really matters to most people listening, but the energy gets higher with higher frequency, because frequency is how often something happens, how often that wave washes into you, basically. So you increase the energy that you're experiencing because you have more waves hitting you. So with like a gamma ray, where a radio wave might only wash over you, like, I don't know, these are obviously wrong numbers, but say it washes over you 1 time per second, a gamma ray might wash over you like 2 billion times per second. So it's not that the amplitude isn't really related here. It's just that there is physically more of the waves hitting you.
No, thank you for the clarification.
Yeah, that's good. Okay. I think that's most of my questions. Peter, any last clarification? I feel like I've learned quite a bit, and
you were about to say any last words, weren't you?
Well, maybe, but I didn't. So, Peter, any last clarifications or any addendums on the material that we presented so far?
No, I feel like you covered it pretty well. Yeah.
Great. Well, I appreciate Peter's insight into physics once again, and we'll have Peter back again sometime. Discuss more physics. Matt and Peter can talk physics, and I can listen and try to understand. But yeah, we'll. For those of you that are listening, we and are looking forward to Matt presenting more about history in the future. We'll do that again sometime soon, right, Matt?
Yeah.
1944.
Yeah.
People are waiting with bated breath.
That is what you are signing me up for, yes.
That's what you get paid for.
Speaking of what I get paid for, if anyone, well, I don't know, are you going to put in your little subscribe plug that maybe we can actually see some monetary compensation?
Oh, you mean the $15 that we currently have is insufficient? Yes. So those of you that have not as of yet followed us on Spotify or whatever it's following on Spotify, like us or review us on iTunes. We've got listeners all over the world. I usually try to give an update on where we stand with with which groups of the country and or world. I think as of late, as I mentioned, we have New York that has really jumped on the bandwagon, and so We also appreciate all our listeners in California. But you know what? Who really moves the needle in a way that I didn't expect is Ontario, Canada. So those of you that listen to us in Ontario, Canada, what is a greeting in Canadian?
The word is thank you, and it's the same in Canadian as it is in English.
All right, thank you. I could sing "Oh Canada," but let's not.
Wouldn't.
Yeah, let's not do that.
I think that would be punishing the users who are listening in Canada.
I had a friend from Canada, and he used to sing "Oh Canada" to me sometimes. And
friendly Canadian? Say it ain't so.
Anyway, but yeah, all over the world, we appreciate everyone that's listening to us. Go ahead and follow us, like us, ask us any questions you have on Facebook, either for Peter or Matt or myself or Cameron or Tim or Johnny, any of us that you've heard on any of these episodes. I will get in touch with them and we will do a follow-up if you have questions for us. But thanks, Peter, again for the discussion of electromagnetic fields and forces, and we will be back again next podcast. Thanks.